Hi, I'm Tomáš Kulhánek from Prague. I was looking forward to meet you in Montreal in this time, but it was not possible. Here in the Czech Republic, the situation with COVID-19 is quite relaxed. We wear face masks. It's obligatory now only in public transport and public buildings. I will talk about our experience in teaching of modeling and simulation with example of glucose insulin regulation model. I'm back now in our laboratory of biocybernetics. It's in Institute of Pathological Physiology, First Faculty of Medicine in Charles University in Prague. And we have tight cooperation with the Czech Technical University, with College and the High Art School of Václav Holar and the spin-off company Creative Connections. We do education. We do educate general medicine students. We do educate biomedical engineering students. And we do educate also the art students. Our current and past projects include Virtual Patient Simulator and eGolem. We teach modeling and simulation, which is part of biomedical engineering here in Czech Technical University in Prague. We teach basic principles. We teach also Modelica language, but not only. We use free open source Open Modelica tool as well as some commercial tools. And we cover some advanced analysis using Python programming language and Jupyter notebooks. This talk is about how we teach to model selected biomedical phenomena. We split the block of seminars into the 8 distinguished steps. We cover 3 different modeling techniques, and in each modeling technique we try to write the same model. And the rest of this talk will briefly follow this schedule and summarize our experience with it. First step is introduction to reality to be model. So in our case, we chose glucose insulin physiology and pathophysiology regulation model, and it can be simplified using this schema. There are 2 compartments, glucose concentration and insulin concentration. And the high glucose concentration triggers increased production rate of insulin, and the insulin concentration triggers tissue utilization of glucose. The second step is how to express equations in Modelica. And for example, this differential equation can be expressed using the derivative of x is equal to 1 minus x. And if we simulate the model from 0 to 1, we have this solution. The glucose insulin regulation model can be described using these equations, which were published first by Stolvik-Hardy in 1974 and Coe in 2000. And these equations can be directly transcribed to the Modelica. Block schema-based modeling is another technique. So in Modelica, I like to express this statement. So it is not expression, it is statement. And the result of this algebraic expression should be put into the variable named y. So I can define the icon where u1, u2 is input, y is output, and in Modelica text I explicitly said what should be done, and I said that the input connectors are u1, u2, and output connector is y. So when combining inputs and outputs from different blocks, I can make more complex models. Model of glucose insulin regulation can be expressed in block schema, and it was published by Coe in 2000, this schema for Simulink, where there are blocks of integrator, blocks of gain, and blocks of summator. And this can be expressed in Modelica using the same similar blocks. Integrator is here, sum is here, and some gain is here. Component-based modeling is another technique which is based on the idea that I have communication points which are connectors. Here causal connectors declare as input and output, but I have also the acausal connector where I don't need to decide what is input and output, and it's decided by Modelica tool upon the compilation. So the variable is declared as flow as non-flow. In this example, the Modelica tool generates Kirchhoff's law of analogy for equations. And there is a component using a causal and causal connector here. Here is the example of model composed by different components. So here I have three components, one compartment, one production flow rate, one volume const, and these are connected using one causal connection and one acausal connection. And these are translated, the causal connection is translated into one equation, but the acausal connector cause that it is translated into the equality for all non-flow variables, but sum of all flow variables here are 0. First, I need to define components before I will make a component-based model. So the table 1 shows the definition of connectors. The table 2 shows the definition of basic components. Previously defined components of production flow rate and degradation rate were abstract. Here are concrete implementation. It differs whether the production flow rate is triggered by constant parameter or is triggered by some input which comes from outside, or if it is triggered by some more complex computation. Using previously defined components, so we can connect the components together and make a model of glucose insulin regulation. So if we compare to this model to the schema in the first slide, it is very similar, and we say that this component-based model follows the modeled reality much better. It's quite time-consuming to define components, but if they are sensitively implemented, they can be shared and they are very reusable and published as Modelica libraries. Modelica standard library already contains blocks mentioned above and also contains SE unit type definition. In our laboratory, we published Physio library, which focuses on physical domains when modeling human or animal biology and physiology. When modeling model of glucose insulin regulation can be expressed in Physio library like here. Last but not least step is customization and advanced analysis. So what will happen if I decrease parameter beta to 10%? So the parameter beta is insulin production rate, and when I simulate and compare to the normal model, then I see that the concentration of glucose is doubled. It's type 1 diabetes. If I decrease parameter Ni to 10% of normal value, Ni is the utilization of tissue dependent on insulin, and if I simulate, I can have the similar result. So the glucose concentration is doubled. So I see the similar manifestation, but from different reason. System identification and parameter estimation is advanced techniques to do system analysis in some modeled reality. Here is the example of Jupyter Notebook where we use Python scripts, and we exported a Modelica model to functional mockup unit, FMU, which can be then executed by Python library PyFME. We follow this schedule when covering different phenomena. As a result, students implement the same model using all three approaches and experience cons and pros of each technique. Equations-based modeling is rapid to implement because equations are usually in literature, but unit conversion is source of errors, and complex models are hard to maintain. Block schema-based modeling is also fast to implement because block schemas are in literature as well. Block schemas are order of computation and not model schema, so it's another source of errors, and complex models are hard to maintain. Component-based model needs to define components, so it is kind of time-consuming, but it leads to understand modeled reality, which is good. Model implementation follows model schema, and there are reusable libraries, which brings more flexibility, and complex models are less hard to maintain. So the students who familiarize with component-based modeling usually do not have problems with advanced analysis and customization. Customization is more difficult for block schema or equation-based only models. Thank you for your attention, and here are the links for supplementary materials.